after our discussion about the independent set problem, I want to switch gears and talk about a problem that involves partitioning a graph into independent sets, traditionally called the graph coloring problem. So, in the graph coloring problem, we are given a graph as input, and we want to color the vertices in such a way that no edge has both of its endpoints getting the same color. So that's the graph coloring problem. It has a long and rich history. It can be traced back to interest in the map coloring problem, where you are given a map of geographical regions and you want to color each region in such a way that two regions that share a boundary are not colored with the same color, because then they become visually hard to distinguish. So you can imagine modeling this like a graph where every region is a vertex and two regions that share a boundary have an edge between them. When you do this, you do get a special class of graphs called planar graphs, and the coloring problem for planar graphs is really, really well studied in particular. And you can find out more about this problem by either looking up some of the links that are there in the course notes or just by exploring it yourself. But I want to just focus here on the general graph coloring problem, not restricted to any specific graph class necessarily. And it is a problem that actually does capture a lot of other unrelated problems, just like with flow, for example. We looked at a bunch of problems that can be modeled as a network flow problem. Similarly, many problems can be thought of as graph coloring problems. So, for example, it turns out that a lot of problems involving creating timetables and respecting constraints related to timetables can actually be modeled as graph coloring problems. And there are several other examples, but I'll not get into those now because I want to turn your attention to a reduction that we are going to actually work through to convince ourselves that graph coloring in general is at least as hard as satisfiability again. And in particular, I'm going to focus on the three coloring problem, which basically says, can you partition the vertex set of your graph into three parts, each of which induce an independent set. Notice that that's the same as the constraint that we started out with, because now in this abstract graph that's drawn here, for instance, notice that if you have an edge, then it must go across these parts, right? Because each part induces an independent set simply means that there are no edges within a part. All the edges must essentially lie across the paths, but that is the same as saying that their endpoints have different colors, right? So whether you think of it as edges having different colors on their endpoints, or you think of it as each color class inducing an independent set, it's really the same thing. So before moving on, let me just write down the definition of a proper coloring formally so that we are on the same page. So a coloring function assigns to every vertex a color, which we can think of as labels from 1 to k. And this function is a proper coloring if for every edge uv, the color that we ascribe to u is different from the color that we set for v. So that's what's called a proper coloring. In general, you might be interested in asking what's the smallest number of colors that you need to actually be able to come up with a proper coloring function for a graph. But what we are going to do instead is really set our target on a specific k. In this case, it happens to be 3. And we want to know, well, can we color the graph using just 3 colors? It's a yes-no question. And well, it might remind you of something that you may have seen when you studied, let's say, applications of BFS, for example. If instead of 3, I ask for whether the graph can be partitioned into 2 independent sets, then that's just a question of recognizing if the given graph is bipartite or not. Because that's the very definition of a bipartite graph, is a graph that can be partitioned into 2 independent sets. And that, it turns out, is doable in polynomial time. That's not a hard problem. But when you move on from bipartite to tripartite, much like when you move from 2 SAT to 3 SAT, there's a sudden jump in complexity. And it turns out that 3 coloring is actually a hard problem. And we're going to do this by actually reducing from 3 SAT once again. So we're going to show that 3 coloring is at least as hard as 3 SAT. And once again, we are faced with this issue of how do we transform a formula into a graph in such a way that the formula is satisfiable if and only if the graph is 3 colorable. So somehow this time we want the colors to carry some meaning or information about an assignment. And how do we do that? Well, one idea is to just maybe associate some meanings with these colors. So let's say that our color palette is green, red, and blue. And we think of these as true, false, and neutral. So the blue color does not carry any meaning, but we want to somehow say that we might have vertices that represent variables, for example, or maybe vertices that represent literals, so a variable or its negation. And if a literal is colored green, then that means that I want to set it to true. So one of the first things we want to ensure is that if you have a vertex that represents the literal x and another vertex that represents the literal x bar, then we shouldn't allow ourselves to color both of them green or both of them red. If that happens, then we don't have a valid assignment to interpret from the coloring, right? If both x and x bar are colored green, that means we are saying, well, set x to true and set x bar to true as well. And that would not make much sense. And that would be the same if we if we color both of them red, that would imply that we want to set both of them to false, which is equally nonsensical. So we want to avoid these combinations by introducing the appropriate edges, right? So let's first get these colors down in the graph using a universal triangle. So we know that this triangle, we are just going to keep it in one corner and we are going to use it for connections as we go along. So we know that any 3 coloring is going to give 3 different colors to the 3 different vertices of this triangle. And just by convention, let's say that the triangle has vertices A, B, and C. Just by convention, we're going to say that whatever color you give to vertex A, I'm going to think of that as the true color. Whatever color you give to the vertex B, I'll think of that as the false color. And whatever color you give to the vertex C is what I will think of as the neutral color. So that's just a matter of convention. It's useful to fix this convention so that we can stick to it as we build out our gadgets. So the first thing we are going to need is some kind of a variable gadget. This will help us actually create an assignment, the semantics for an assignment. Let's not worry so much about how to make it satisfiable for now. That's going to be the next phase. But for now, I just need to be able to read off an assignment from a coloring. So how do we do that? Well, now that we have these semantics in place, let's say that a variable is simply going to be represented again by an edge whose endpoints I think of as x and x bar, just like we had previously for the independent set reduction. But now if we just leave it at this, we have a problem, because now, for instance, a 3 coloring could color x blue and x bar green, but I don't want that situation. I want x and x bar to be colored either green or red, but not blue, so that I have a clean semantics on what the coloring means as an assignment. So to avoid x and x bar getting colored blue, the simplest thing to do would be to just add edges from x and x bar to the vertex C. This way, we ensure that X and X bar don't pick up the color that is assigned to color C by any 3 coloring, but we have already agreed that we are going to refer to the color that the vertex C is colored with as the neutral color. So the neutral color is automatically avoided on both X and X bar. So what we are going to have is a bunch of these variable gadgets coming out of the vertex C, and all of them are going to be colored with green and red. In some cases, X will be colored green and X bar will be red, and in some cases, it's going to be the other way around. So now we have a clean read of an assignment, and now we have to somehow ensure that, whatever assignment the coloring is asking us to consider is actually a satisfying assignment. And for that, of course, we have to somehow encode the information about the structure of the clauses in the formula into this graph. So we are going to do that with the help of a clause gadget. And what we want to do is design a gadget which has the property that it forces a situation where if the assignment we had on the variable gadgets is not satisfying, then the design of the clause gadget should be such that it raises a complaint. It says that, look, because of what you have done there, I am not properly colorable anymore. So for instance, let's say that your clause is X, Y bar, Z, right? We need to build something out of this that connects to the variable gadgets corresponding to the variables X, Y, and Z, and basically make some noise if the variable gadgets are not appropriately set. So what are we afraid of? In this case, we are afraid of X getting colored red, Y bar getting colored red, and Z getting colored red. We want this color combination to be avoided. We want this color combination to somehow raise a contradiction. So let's say, for instance, that we try the following. Remember, we have a green vertex in the universal triangle. This was the vertex A. So let me just bring in the vertex A into the picture. Of course, a simple thing to do would be to say that, okay, we connect these variables to A through a subdivided edge, meaning we take one hop and come to A, and let's say we impose a triangle here. Notice that now this all red coloring on X, Y bar, and Z is not really extensible because remember, you only have 3 colors to play with. So each of these vertices in the middle is forced to get the neutral color, because if it gets either red or green, you get a violation with either the vertex A or the vertices from the clause gadget side, right? So that will, by the clause gadget, you're going to have a violation. Okay, so maybe let me make that explicit. If I color this vertex red, then this edge here will prevent this from being a valid coloring. And if I color this vertex green, then this edge will prevent it from being a valid coloring. So we know that the only colors that these intermediate vertices can get is blue, but we have edges between the intermediate vertices which make the choice of blue for all of them to be not valid either. So we are kind of stuck. We are forced to use blue, but we cannot use blue because of the presence of this triangle right out here, right? So this definitely ensures that we don't color X and Y bar and Z red, because it creates this problem. But is this a valid clause gadget? I'd encourage you to take a moment here and think about this. And if you discover that there's an issue with this construction, I invite you to play around a little bit and try to fix it on your own before returning to this discussion. Okay, so I hope you had a chance to think about that a little bit. The issue with this construction is that it is in some sense too aggressive. It does block out the color combination that we want it to block, but it also disallows legitimate color combinations which would be valid. So for example, maybe you set X to true, and that actually satisfies this clause. And now you have a little more degree of freedom. You don't have to color this intermediate vertex blue. You can in fact color it red. But for the other two, we are still forced and stuck with the blue color. And because of this edge here, we still don't have a valid coloring, even though we have a valid assignment. So you have to do sort of this delicate balancing act where you have to create a gadget that blocks out exactly what you want to be blocked, but it's actually permissive on everything else. So we'll have to try something a little bit different here. Let's keep the same example. We have X, Y bar, and Z. Remember, these are vertices coming in from the variable gadgets that we have already drawn. I want to focus on the literals that actually belong to the clause under consideration. So I have a clause. Let me say that this is the jth clause, which happens to be X, Y bar, Z. And I'm trying to build out the clause gadget here. And for me, the starting points are going to be these literal vertices from the variable gadgets. Now I'm going to actually draw up a construction here for the clause gadget, and it may seem a little magical at first sight, and you might wonder, how do people come up with such constructions? It's a simple construction, but it's still perhaps not obvious how you would conjure up something like this. And the best answer I have to that is just practice, and having seen a lot of reductions helps, because it sort of, you start to see that there are some standard kind of ideas or tricks that are kind of recurring, which you can adapt to your own specific situations. So that preamble, let me actually draw the gadget. So we are going to have a triangle here, and we're going to have Z actually feed into another triangle. And at this point, I want to say that this here is actually a special vertex. This vertex here is the green vertex A from the universal triangle, just like we had here. And once again, let's confirm that, well, that's the entirety of the clause gadget. Let's confirm that if we set all these literal vertices to false, then we are in trouble. Well, indeed, as before, the coloring that we have on Z and the fact that we have A sitting on the other side, which is a green vertex by convention, is going to force this vertex here to get a neutral color, right? Because that's really the only choice we have here. If you again try red or green, you're going to get blocked out from either the left or the right. But now that this is the neutral color, the only choice we have here is to use red. But now notice that we have this triangle sitting here in the middle, sandwiched between red on all sides, which means that inside this triangle we cannot use red. It's blocking all of the vertices. So we have to manage to color a triangle with only two colors, but that's clearly impossible. So the all reds coloring again does not go through. It's not extensible in the presence of this gadget. But now what you want to convince yourself is that if one of these vertices was colored with the good color, the color green, then you can actually extend this to a valid 3 coloring. And indeed, in this case, you can perhaps convince yourself that, for example, you can use the color green here. You can use the neutral color blue here, and you can use red here, and that's a perfectly valid coloring. If the green was on y bar instead, then that would be similar. If the green was on both x and y bar, that would also be fine, because then you could use blue and blue and red on this edge here, and then over here you could then use green to match up with the red blocker on the other side. So if either x or y bar or both were green, then you're happy. If z was green, then you're happy as well, because then you can color this vertex red and this vertex with the neutral color instead of what we are doing now, and then it's easy to percolate this backwards no matter how x and y bar are set. And that's a case analysis that I'm leaving for you as an exercise. So the design of the clause gadget is really made to ensure that if you have all reds on the three literals that appear in a clause, then this gadget gets stuck and there's no way to properly color it with three colors. But if there's at least one of these literals that is set to true, then you can always extend the coloring to a valid coloring of the whole gadget. Okay, so that's kind of the property that this gadget enjoys. So let me just recap what the sort of the overall construction looks like. So we have at the heart of it a triangle, and we gave our own semantics to the colors of this triangle. So for instance, we said, well, one of these colors we're going to call a neutral color, one of this is our true color, and one of these is our false color. And then we had the variable gadgets just basically coming out of the true color like that, and that basically forced each variable to agree if the x is going to be true and x bar is going to be false, or the other way around, depending on how these vertices were going to be colored. But what this connection with the blue vertex ensured is that for every variable gadget, you only get to use the green and the red colors, the true and false colors, on the two vertices representing the literals of x for any variable x. So that was the variable gadget. And then we sort of had a clause gadget, which was this black box, which is connected to, on the one hand, the green vertex, and on the other hand, it also has connections to the literals that belong to it. So the clause gadget basically forced that whatever assignment we read off from the variable gadgets is actually a valid, satisfying assignment, right? So just very quickly, there are two parts to proving the equivalence. On the one hand, we want to say that if the formula has a satisfying assignment, then the graph that we have constructed is three colorable. But that's really quite straightforward. When you have your satisfying assignment tau, you just color the variable gadget vertices according to tau. So if, for example, if tau sets x to true, then the x vertex gets the green color and the x bar vertex gets the red color. But if tau of x were to be false, then it's the same thing, but just the other way around. So x would get the red color and x bar would get the green color. So that's an assignment of colors to all the variable gadgets. And as far as clauses are concerned, you just look at what the situation is and percolate the colors forward based on the constraints that you have. And that's the case analysis that I said I'm leaving as an exercise. You can check for yourself that no matter what the assignment is, as long as it's not the all false assignment, you will always be able to extend this coloring to a complete coloring for the rest of the gadget. So there are these 5 additional vertices that you'll need to color, and you can always do it in a manner that's feasible. Now, the second part of it is that if there is a 3 coloring, then you can recover a satisfying assignment. And of course, as we have discussed several times by now, by just looking at how the variable gadgets are colored, you can read off an assignment. If x is green, then x is true. If x is red, then x is false. That's essentially the assignment. And you want to argue that this assignment is a satisfying one. And you can argue this by contradiction. You say, suppose not, then there is a clause which is falsified. And if that clause is falsified, that means that if you look at the clause gadget, it really should have been stuck by an argument that we made while we were coming up with the construction. It's really that argument at play here. So if a clause was fully falsified, then the 3 coloring is simply not valid, on restricted on the vertices of the clause gadget corresponding to the falsified clause. So that's essentially a bit of a hand-wavy argument for the proof of equivalence of these 2 instances. I really encourage you to either skim through the notes a little bit or try to work through this yourself to be sure that you have all the details right. One thing that I'm certainly leaving as homework is to figure out all the cases in the forward direction to make sure that if you have a satisfying assignment, you can actually extend the coloring on the clause gadget. So we've shown that 3 coloring is as hard as satisfiability. It's not hard to show from here that K coloring is hard for any K that's at least 3. You can go from 3 coloring to 4 coloring and so on and so forth. And that's not very hard to show, and that's also a fun exercise to think about a little bit. On that note, that's a wrap as far as graph coloring is concerned. The next problem we'll be looking at is 3-dimensional matching. And it's again one of those things where you see a jump from 2 to 3. If you wanted a normal matching, then finding a largest matching in a graph is famously polynomial time. But once you want something that's just a little more general than a matching, it turns out to be hard. And that's what we are going to explore in the next video. So I'll see you then.